Hello, I'm Sean Grady, and I'm a senior software architect at Rocket Software. Today, we'll be talking about addressing scaling and availability with Containerized Zowe. So, this discussion is really just about how we can use the server components of Zowe in different environments. It was the case before that when you installed the Zowe server components, they must go on ZOS. But throughout this year, we've been exploring with different ways in which we can distribute the Zowe servers. You can still use ZOS as your place to put all of Zowe, but we're providing different options using containers so that you can exploit the features that they have for scalability or fault tolerance. So, first off, I'll introduce the concept of containers, and then we'll take a look at what we've done so far with containers and what we'll do next, and pull it all together with some examples. So, when it comes to containers, I'd first like to focus on the server components of Zowe. So, Zowe really is a collection of frameworks that help you to interact with the mainframe in modern and intuitive ways. And some of those are servers, some of those are client applications. But when it comes to the servers are helping to power those client applications. And some of them are very low level on ZOS. They do system calls and they really need to live on ZOS. But there's this question of, well, do all of the Zowe servers need to run on ZOS? And it turns out that over half of the Zowe servers are actually operating at the network level. And so they're utilizing either the callable service servers or other servers on ZOS, such as ZOSMF. So for these network level servers, they could possibly run in different places. And that's when we started looking into if containers could be a viable option. And so, what if we could move those higher level servers into a different location? Well, that's how we get into the concept of containers. So, containers are really a packaging of a program and its dependencies into a single deliverable, a lightweight standalone executable. The deliverable itself is a read only source from which you make a runtime container. And the nice thing about containers versus, say, a virtual machine is that really, when you look at virtual machines, they would contain an entire operating system and potentially run multiple programs. But really, a container is at its best when it only runs one program and it actually doesn't have the operating system itself being virtualized at all, but rather that application inside the container is running using the host OS. So it's a little bit leaner and it is easy because all of the dependencies that you need are inside of the container. And it's also reliable because since everything is packaged in a deliverable, then you get the same behavior no matter where you're deploying this container. So when we look at software running with or without containers, we encounter a few different models in which you can package your software. Without containers, let's say the Zowe case in which all the servers are running on ZOS. We have a few different components of Zowe, A, B, and C, for example. And if we install them onto the ZOS file system, we're first going to need some prerequisites. So we're going to need to download and install Node.js. We're going to need to get Java set up. And the portability is a little bit limited because if we go to a different system, we'll need to do the same thing. The scalability is also a little bit more complicated because the servers have their own nuance, and so you need to understand a lot about how they work in order to make sure that you have the scalability set up correctly. However, when you move to a container model, more of that is standardized, more of that is handled for you. So in model number 2 here, this is what we have with the tech preview. No prerequisites are needed because they're bundled inside of the container. However, we're bundling all of the servers into one container here. So we run into a different problem, which is that if one of the servers has an issue and it needs to be restarted, this container is all or nothing. We would need to restart all of the containers, or we would need to restart all of the servers from an external's perspective. Same thing with scalability. If, for example, the mediation layer needed more throughput than the desktop, well, there's no standard way to scale just one of the pieces inside of the container. It's considered a single unit of scalability from external tooling. So if we want to leverage the ability to do intelligent restarts and intelligent scaling, what we need to do is we need to have each of the servers in their own container. And so this is what we aim to do with Kubernetes, where we'll take each of the Zowe servers, put them into their own container, and then tie them together with shared configuration and utilize the power of Kubernetes orchestration to help us manage the lifecycle and maintain the status of all of these servers. Now, going back to the ZOS picture, using ZOS is still going to be a viable option, and so you really want to know, how does this change the Zowe ZOS story if containers exist in the future? If you're already using Zoe and ZOS, really nothing changes for you at all. The configuration, the documentation, the installation, all of this stuff is the same as before. However, if you were to make use of the containers, then things change a little bit. So the parts of Zoe that you install on ZOS, even with containers, remain the same. It's going to be the same installation steps for ZSS and ZIS. However, after you set those up, you would configure the ZOS instance to simply run less of the other servers. So you don't need to run the mediation layer or the app server on ZOS if they're running in the containers instead. Then things change from that point on, because the containers are going to have their own setup. So the ZOS story without containers doesn't really change at all. With containers, it's basically similar, but there's less going on because the rest of the servers have moved to containers. So let's do a quick review of what we initially did when we were looking at containerization for Zoe. In the first quarter, we launched what we called a tech preview of containers, and it's available right now on zoe.org and Docker Hub. Some people used it, and it was a pretty good proof of concept to show how we could put the Zoe servers into Docker, but there were some limitations in how you could use it and where you could use it. We didn't get around to ZCX yet, and things like key rings are still in the works. But the ultimate fate of it is that we didn't get too much feedback. All the feedback that we got was positive, but the feedback was limited due to it being called a tech preview, and people wanted to wait for the general availability release. However, it wasn't too much work on our end to pull off. Essentially, what we did was we took a traditional ZOS release of Zoe, and we took the parts of the servers that could live on different systems and packaged them up inside of a Docker container, converted all of the text from EBCDIC to ASCII, removed any ZOS specific flags to how Java or Node.js would be invoked, and then hard-coded the paths for where you would find the Zoe installation folder and where you would find the key store and where you would mount your own instance directory. It included all the dependencies that you needed, and even third-party products and components could be mounted into the container without modifying the state of the container itself by using a volume mount. So what we learned when we did all of this is that there are many different ways that we can distribute Docker once we've created it, and choice is good. At first, we thought that we would just host the content on Docker Hub, but it proved that a lot of people also wanted it to be available on other registries or directly off of Zowe.org. So we ended up doing both Zowe.org and Docker Hub downloads. Security wise, we learned how to adhere to all the best practices with distributing Zowe via Docker. And so we know going forward that we want to keep dependencies minimal whenever possible. Less software inside of the image makes it easier for us to maintain with the ever increasing complexity of security in the world. Image signing is another way to verify that the container you're getting really came from us. And ultimately, there's more that we can do when it comes to documentation to make sure that people are fully aware that when you're using containers outside of ZOS, you not only need to keep your ZOS security optimized, but you need to be pretty good at Linux security as well. Now, the documentation didn't really change too much, and it was for the best that we emphasized what was similar and then just documented what was different between using Zowe on ZOS versus Docker. We also learned a little bit about how products built on top of Zowe would need to change in order to have Docker compatible versions. So encoding is something that there's really no workaround. That if you want to have a piece of code that can run on ZOS and on a container, you're going to need to deal with encoding. Some code might need to be in EBCDIC on one platform and ASCII in another. Distribution-wise, there are different ways that you can get code running in a container. You could bring your own container, or you could just have files that are mounted into the Zowe container itself. So we took a look at that and we were thinking, well, what's best for the end users and the developers. Scripting-wise, we tried to keep the container as close to the ZOS environment as possible in terms of like how it's configured, what scripts run, how it logs, all of that, because it makes it less different for users that are moving from one installation to another, and it also makes it easier to maintain. But ultimately, one of the most important lessons that we learned is that there's a limitation with putting all of the servers into one container, which is it's difficult to use high availability tools and do horizontal scaling. So when considering Kubernetes, we now have to change our container technology a little bit by splitting up each of the servers into their own container. Each container is going to have the dependencies that an individual server needs, but common Zowe scripting is going to be shared on a volume mount. So each of the servers doesn't need to necessarily have their own copy of Zowe scripting, but there will be a common volume shared between each of them. So this is going to be a best practice approach to make the containers Kubernetes compatible, and each instance of this collection of servers is equivalent to the previous tech preview that we had without any limitations. But utilizing the Kubernetes technology can handle the management of restarting servers if they need to be, or scaling out the servers. If I need 5 copies of the desktop and only 1 copy of the API catalog, or vice versa, that's possible with this technology because we split up the servers into their own reusable containers. So this is just another view of the same thing, really, that rather than having one big server, or one big container with many servers, we now have several containers, each with their own server inside of a unit known as the Kubernetes Cluster, in which it can manage the duplication and lifecycle as needed. And that cluster can be on a different system, but ultimately it's going to need to contact the ZOS sysplex where ZSS, ZIS, and even ZOSMF would be located. The different ways we can package Zoe servers into containers likewise result in different ways in which products built on top of Zoe need to interact with these containers. So in the previous model where all of the servers were in one container, the products built on top of Zoe had the option that they could also run in that container. But again, this isn't good when you're trying to do horizontal scale out. This isn't good if you're trying to have each container represent a single server in case you need to monitor its lifecycle. So when we have the Kubernetes environment, we really want every server to be its own container, which means that products also need to be their own container. Now, again, these products need to be ASCII instead of EBCDIC. And again, if you have ZSS or ZIS content that you're interested in, if it's just the server itself, it's still accessible over the network on ZOS. But if you have a plugin for ZSS or ZIS inside of your product, then basically you need to make that available on ZOS. Now, when it comes to the desktop still needs to see those plugins as well. So there's a small bit of duplication in which the desktop must know what ZSS has available. So you need to have the plugin metadata in both places. But that can be just about it in terms of what you need to share to the desktop. Basically, you will have desktop plugin files presented over a volume mount to the app server container. And unless you have services that must also run in the app server, that's it. But if your plugin does include app server services, not only will those files be visible over the volume mount, but the files will actually be running inside of the same container as the app server. As for the mediation layer, there is the ability to have both static and dynamic registration today for having a server being visible to the mediation layer on ZOS. However, in a container environment, it's a little bit more complex in that your server will be naturally in a different location than the mediation layer server because each one is in a different container. So dynamic registration is going to be much simpler because it will allow you to contact the mediation layer over the network. However, we are still going to make static registration possible, but this is something that's still on the roadmap. At the end of the day, we need examples to show you what are the best ways to make your products compatible with containers. And so we do have an example of how to do both desktop and mediation layer integration by using one of our own components, the JES Explorer. So take a look at the JES Explorer to see how did we make a container for it. So when it comes to the do's and don'ts of how to make a product that's dependent on Zoe into a container, we're coming up with a conformance program to make it easy to understand what is the best practice and what you must do. First of all, there's no question that if your product supports containerization, it must itself be a container in order for it to effectively work in Kubernetes. So you would have a container edition of your product, and if your product also lives on ZOS, you would have an archive version. Now, inside of the container images, in order for everything to work nicely, there needs to be standardization. So one of the things that we'll be standardizing is the folder structure. Where do you put your configuration files, such as plugins that you want to share with the desktop? Where do you put the static registration files? There's even standardization about what the server user should run as. It should be the username to Zoe. So there's a lot of standardization that we need to have here in order for things to work nicely. And one of the things that we're doing to make this easier is to make Zoe provided conformant base images. When you make a container, you can choose a base image for the container to be based upon. And so we've made Ubuntu and Red Hat UBI containers with or without some of the prereqs like Node.js and Java that already have certain things done for you, like the user Zoe is already created and the standardized folders that you'll need already exist. Um, Now, there are also some best practices in the standards that don't really affect how the code behaves, but will just make it easier for users to understand what's going on, such as the naming scheme and versioning. If you have a Linux on Z version of your container versus an Intel Linux version of your container, you're going to want to name them appropriately so people understand that. Now, it's not just about a conformance program of saying what you can and can't do. Farther down the road, we're also going to be utilizing these standards to make it easy to provide the vendors and extenders with scripting that will make it easier to make containers and to make the containers easy to set up and use. So one of the things that we'll be doing is we will be standardizing how static registration of servers would be presented to the mediation layer, or how iframe plugins would be presented to the desktop. We also know that in the case of a ZSS plugin, that plugin needs to be presented to both the app server container and ZSS running over on ZOS. So perhaps there will be an easy way in which a user can do one command to have that file end up in both places. Now, in order to get Zoe into Kubernetes and make it maintainable and easy to understand, there's a few steps that we're currently hard at work on, including making it so that the scripting that we use on ZOS today can be reused as much as possible to be intuitive and ultimately easy for us to maintain. But we also need to take the servers that we have and split them up into individual containers so that they run independently, which is already done by developers today, but we just need to formalize it so that these run in their own containers. Ultimately, once we do all of that, we need to have YAML files that Kubernetes understands that serve as samples to our end users to get up and running quickly. And so I'd like to show a little bit about what these samples look like, so that when you get Kubernetes, it'll be easy for you to get running. So here's our Kubernetes examples so far. And what you'll see already is that Kubernetes configuration files are in the YAML format, and they describe various things such as resource requests and how to satisfy them, and ultimately how the containers that you want to run interact with those resources. So we're going to have Zoe ship with some sample config files that make it quick and easy to get Zoe running in this environment. And you'll see in the app server below that we list things such as the name, the image that it comes from, the port that it runs on, and even the volume mounts for things like plugins and the configuration. So a lot of this is plain text, but we're going to add some documentation to make it easier to understand. But the nice thing about these configuration files is that you can use tools such as kubectl, which is a CLI tool for managing Kubernetes clusters, and you can do a command apply on these files to sort of add this configuration to your Kubernetes environment. And in the case of these deploy objects, as soon as you add them, Kubernetes can be set up to start up your servers. So in this example, I just did an apply on an entire folder of deployment files. And as soon as I did that, I can see my deployments with the git deployments command. And finally, I can see with the pods command that the pods, sort of the unit of containers for Kubernetes, the pods start from the deployment as soon as possible. And it looks like they've all started and have unique IDs that I can analyze farther, such as together logs. Now, it's not just about the command line either. Once you have Kubernetes set up, you can have wonderful UIs to look at. And in these UIs, you'll get to exactly what you're looking for quite quickly. And one of the things that you'll find in the case of Zoe is that there's more in common than there is different in this environment. So first of all, you'll see that Zoe in Kubernetes has a similar config to what we have on ZOS. What you're looking at right here is contents from the instance env file, which is what we use on ZOS today to manage Zoe configuration. So it's still there, even in the Kubernetes case. So are the logs. If you've ever looked at the job output from Zoe, you'll see that the logs have formatting that talks about which component is running and what user they're running as. In Kubernetes, it's always going to say the user Zoe, but pretty much everything else is going to be very similar to what you see on ZOS when it comes to the logs. However, one of the things that's a little bit different is that since Kubernetes is so standardized, once you have everything up and running, it's very easy to monitor the status of things. So what I'm looking at here is just the set of Zoe servers that I put inside of the namespace Zoe. And now I can see, well, what is the overall CPU usage that Zoe is using? What's the memory usage? And how's the status of each of these things? And it really just goes on and on from there. There's tons of metrics that you can pull once you have Kubernetes set up, so you can really inspect, how is Zoe doing? Do I have enough horizontal scaling to meet the needs? Do I have enough hardware to meet the scaling that I want to do? So yeah, Kubernetes really helps you to monitor the bigger picture. Moving on past that, there's still much more that we want to do in the future. So after our initial release, you should also be on the lookout for things such as different places that we can host our containers, signing the containers and how to verify that. Helm chart is another technology we can use to simplify the configuration even farther to make up and running a breeze. Certificates, certificate authorities, the whole key store setup. There's always more ways in which we can educate and potentially automate how to set up certificates, especially in the Kubernetes environment. There are even other platforms for containers that we will target in the future, such as OpenShift and ZCX. High availability. One of the strengths of Kubernetes is something new to Zoe, and so we just have to make sure that we document and explain how you pull it off in a Kubernetes environment also. And then we have to figure out, going back to the tech preview Docker where all the servers are running in one container, what happens to that? Do we keep it around, or does the Kubernetes technology just prove superior in every way and we just go with that? But ultimately, the things on this list, some of these things we must do, some of these things are up to you. So you tell us what you want, and we'll prioritize based on that. So if you're interested in getting in contact with the Zoe community, make sure to check out zoe.org. It really has all the links you need. There's many ways to get in contact with us, but the website's got all of them. You can also check out our Slack, which is where all of us are communicating. There's community calendar, so you can catch all of our regular meetings too. And of course, there's always the GitHub, in which you can, file tickets for feature requests or issues that you found, or even contribute, and that would be great too. So that covers the status of containers and what they will be in the future for Zoe. Thank you.